So these are the solutions to hypothesis testing for means and sampler proportions. So question 2 is the first one. The editor of a weekly magazine is concerned about typographical errors and believes that about 1.5% of the number of lines printed will have one error. An examination of 650 randomly selected lines revealed 11 lines had one error. So that's a proportion, right? 11 out of 650. Does the sample support the editor's belief? Use a 5% level of significance. So we set up a hypothesis test for a proportion, which means we have to do a confidence interval test. Okay, null hypothesis is that the proportion H0P proportion is equal to 1.5% or 0.015. So 1.5% of lines printed will have one error. And then the alternative hypothesis is that the proportion of lines does not have 1.5% of errors. Okay, or sorry, that 1.5% of lines do not have one error. So make sure you do write the sentence beside that as well. Okay, so p hat is 11 over 650, or you can write it as its decimal equivalent. We set up the confidence interval, so the true proportion p lies between the lower interval of p hat minus the margin of error and the upper interval of p hat plus the margin of error. So here's the kind of a separate calculation for the margin of error, 1.96 for a 95% confidence interval by the square root of p hat, which was 11 over 650, by 1 minus p hat all over n, which is 650. And that works out to be 0.009916. That possibly goes on forever. Don't round up. So I'm just subbing that into the confidence interval formula. So it'll be p hat. Again, they're leaving it in decimal format. You can leave it as the fraction, which was 11 over 650. But anyway, so it's p hat minus the margin of error and then p hat plus your margin of error. So that tidies up to be the true proportion lies between 0.007 and 0.02. Okay, you can write them as percentages if you want. So that would be 0.7%, and that would be 2.68%. So because p was 1.5, okay, or 0.015, that lies within that interval on a number line. So because your true proportion lies within that interval, that would mean that we fail to reject H0. So we're concluding then that 1.5% of the lines printed would have one error. So the company's claim was correct. Question 4. Suppose you interview 1,000 randomly selected exiting voters following a presidential election. Of the 1,000 voters, 550 reported that they voted for John F. Murphy. Assuming that there were only 2 candidates in the race, is there sufficient evidence to suggest that Mr. Murphy will be the next president? Use a 5% level of significance. So again, this is going to be a hypothesis test for a proportion. So p hat will be 550 over 1,000. Okay, now, because there's only 2 people in the race, and in order to be the next president, you obviously have to get more than 51% of the votes to be the next president. This will only be a one-tail test. So your null hypothesis, the null hypothesis P is going to be greater than 50%, right? So 0.5. So more than 50% of voters would have voted for Mr. F. Murphy. The alternative then is that the proportion is either less than or equal to 50%, because if it's equal to 50%, well, then it's a split vote. If it's less than 50%, well, then obviously he doesn't become the next president. Okay, so we set up our confidence interval for a proportion. So the true proportion would lie between lower threshold and the upper threshold. So remember, p hat was 550 over 1,000, which is 0.55 as a decimal. So we're just subbing that in to our confidence interval formula. And you eventually get out, the true proportion lies between 0.5192 and 0.5808, which as percentages is 51.9 and 58.1%. So obviously then our confidence interval of 0.5, 50%, would suggest that he would be the next president. So the confidence interval suggests that Mr. Murphy would get between 51.9 and 58.1% of the vote. Okay, so he's gotten more than 50%, and that's what we wanted it to be in order for him to be elected the next president. Question 6, and we're doing part 2. The following z-scores were obtained in a selection of 2 tailed hypothesis tests. Give a p-value for each of these. So these were the test statistics then. Okay, so 2.45 is your z-score. So basically to find the p-value, it's the probability that an even more extreme value than 2.45 occurred. Now, given it's a two-tailed test, that means we have to check for values that are less than minus 2.45 and greater than positive 2.45. Okay. So I'll do the workings actually beside this just to show you where exactly I'm getting that first original formula. Okay, so you're checking on either side. It's a two-tailed test, so the probability of Z being less than minus 2.45. So based on symmetricality, that would be the same as the probability that Z is greater than 2.45. You can't get greater than, so that's the same as saying 1 minus probability that you're less than. And the same then for here, being greater than is 1 minus probability that you're less than. Tidying that up, 1 plus 1 is 2. Minus the probability of that minus the probability of the same thing gives us minus 2 times the probability of Z being less than 2.45. Go to your Z tables, get out your probability for 2.45, which is 0.9929. Multiply it out and you'll get back your 0.0142. So that's your p-value. Because your p-value, 0.0142, is less than the significance level of 5%, you would reject H0. Part 4 was a test statistic of 2.92. So it's going to be the probability that Z is less than minus 2.92 or the probability that Z is greater than 2.92. Again, use symmetricality. Being less than minus 2.92 is the same as greater than 2.92. You can't get greater than, so that's 1 minus probability of being less than. And the same for that, 1 minus probability of being less than. Tidying that up, you'll get 2 minus 2 times the probability that Z is less than 2.92. Go to your Z tables, get out a Z score of 2.92, which gives you back a probability reading of 0.9982. Sub it into your sum here, and it works out to be 0.0036. So because 0.0036 would be less than your significance level, you would have also rejected H0. So that's part 4. Part 6 was 1.15. So it's probability that Z is less than minus 1.5 plus the probability Z is greater than 1.15. Okay, and again, when you tidy all of that up, go to your Z tables, find the probability of Z being less than 1.15 and you'll get 0.8749. And again, that will give you back an answer of 0.2502. So given that your p-value is greater than your significance level, you would therefore fail to reject H0 for that one. Part 8 was 1.82. So again, being less than minus 1.82 or being greater than plus 1.82. Tidy it all up, go to your Z tables, get a probability that Z is less than 1.82, which gives you back 0.9656. Tidying that up, you'll get 0.0688. So given that 0.0688 is greater than your significance level of 5%, you would also fail to reject H0 for that one. Number 7, a particular machine produces metal rods that are normally distributed with a mean length of 210 centimetres, so that's mu, and a standard deviation of 6, that's sigma. The machine is serviced. Following a service, a random sample of 100 rods, that's n, is taken, and the mean length of the sample is found to be 211.5, that's x bar, with a standard deviation of 6, so that's still sigma. Is there evidence at the 5% level of significance of a change in the mean length of the bars produced? All right, so we do a hypothesis test for a mean, so we'll have to do a test statistic. And then when we've the test statistic got, it's asking us to give a p-value for this hypothesis test and then interpret that p-value. Okay, the null hypothesis is that mu is equal to 210, so I should put in mu in there. So that would mean that there is no change in the mean length of the bars that were produced. It stays as it was. Whereas the alternative hypothesis H1 would be that mu is not equal to 210. So the mean length of the rods has changed. Okay, so next step we set up our test statistic. So Z is going to equal x bar, which was 211.5, minus mu, which is 210, all over sigma, which was 6, and n was 100, so root 100. And that works out to be 2.5. Okay, so draw your quick sketch of your critical regions. So this would be the fail to reject region, whereas these two critical regions here and here, they're the reject regions. So because 2.5 on a number line would fall into this region in here, that means we will be rejecting H0. So as 2.5 falls into that critical region at the 5% level of significance, we reject H0. And what can we conclude from that? So we're rejecting their claim that there was no change in the mean length, which means there obviously was a change. So we conclude that a change in the mean length of the bars had been produced. So there was a change. The next part then said go and get a p-value for that. So the p-value is the probability that an even more extreme value than your test statistic could have occurred. So I want to be greater than 2.5 or even more negative than minus 2.5 because it is a two-tailed test. Okay, so we set that up. It's the probability that Z is greater than 2.5 or the probability that Z is less than minus 2.5. Or means plus in probability. Tidying this up, being greater than 2.5 is the same as saying 1 minus probability of being less than. You cannot get negative values, so that's based on symmetricality. That's the same as being greater than 2.5. And again, you can't get greater than, so that's the same as saying 1 minus probability that you're less than. When you tidy that up, you'll get the following. You can now go to your log tables, find a z-score of 2.5, and it should give you back a probability of 0.9938. And subbing that in, you should get 0.0124. So that's 1.24%. That's less than your significance level. So because it's less than the 5% significance level, you would reject H0. And we had already rejected H0 when we did the hypothesis test, which means this is further backing up our claim. So it says, what can you interpret from this? So as the p-value is less than the 5% significance level, we reject H0. So the mean length of the bars produced is significantly different from previous. Question 8. The mean mark for all students taking a certain Leaving Cert exam or subject in the higher level 2012 was 67.5 with a standard deviation of 10. Okay, so there's your mu and your sigma. A random sample of 100 students, that's N, who sat the Leaving Cert in that same subject in 2013 revealed a sample mean of 69, so that's X bar. Is there evidence to conclude that the students have improved in a year? So basically, has their average changed? So it was previously 67.5. Has it now changed from that? Assume 2012 and 2013 exams were of equal difficulty. Okay, so we're going to set up a hypothesis test for a mean. The null hypothesis is that mu is equal to 67.5, which means there was no change in the mean mark of students in that particular subject, whereas the alternative hypothesis, H1, which would be mu is not equal to 67.5. And again, write your sentence that there was a change in the mean mark. Okay, get your test statistic, sub into your formula, and you should get out 1.5. Draw your quick sketch. 1.5 is going to lie in here. Okay, so based on your number line, and it's a 95% confidence level or 5% level of significance. So it would be roughly around there. So we fall into the fail to reject region. So the two critical regions are the reject regions, but this is the fail to reject region. So therefore, as 1.5 lies outside of the critical region at the 5% level of significance, we fail to reject H0, which means we technically have to accept it. So we're accepting the fact that there was no change in the mean mark. So we can conclude there was no change in the mean mark as suggested by the evidence. Question 9. A random sample of 106 body temperatures had a mean of 98.2 degrees Fahrenheit and a standard deviation of 0.62 degrees Fahrenheit. Use a 5% level of significance to test the claim that the mean body temperature is not 98.6% or degrees Fahrenheit. Give a p-value for the hypothesis test and interpret that result. Okay, so mu is your 98.6. You have your sample size there was what? 106 body temperatures. Your standard deviation is your 0.62. And then you have your mean there of 98.2. Okay. So the null hypothesis, mu is equal to 98.6. That would mean there was no change in the mean body temperature. The alternative hypothesis is where mu is not equal to 98.6, which means there was a change. And you write in that sentence. So we set up our test statistic for a mean, and when you sub it all in, you should get back minus 6.64. So draw your quick sketch. Okay, you have your two reject regions out here, the two critical regions, and you have the fail to reject region in the middle. So minus 6.64 would lie somewhere off down here. So I'm in the critical region, which means I am going to reject H0. So as minus 6.64 lies in the critical region at 5% of significance, we reject H0. So what can we conclude from that? We are rejecting the fact that they said there was no change in body temperature. There obviously was a change. So we conclude that the mean body temperature is not equal to the 98.6 degrees Fahrenheit. It has changed. Okay. Then it says go off and get a p-value for that. Right, okay, so it's probability that an even more extreme value than our test statistic could have occurred. Now, you'll notice in your log tables that you're not going to be able to get a test statistic or a p-value for this because 6.64 being more positive than 6.64 or even more negative than minus 6.64. Your z-scores only go up as far as 3. So you actually won't be able to calculate that. Don't worry too much about that. They'd never give you something like that in the exam papers where your z-score tables in the log tables don't even go as far as that number. Okay? Because I suppose if it did, you'd be starting to think, have I made a mistake? Right? But anyway, because we are going so far out to being even more extreme than minus 6.64 or more extreme than positive 6.64, you could nearly say it's almost all the data, okay, between those two intervals. So that's where they're getting, like, you know, the probability of being two-tailed test. Eventually they'd say it was 99%. So 1 minus your 99%, 99.9% is 0.01 of a percent. So it's pretty much non-existent. But anyway, so therefore your p-value would be less than your level of significance, okay, which means we were right to reject H0 when we did in the first place. And then just put that into a sentence. So we are supporting the company's, we are not supporting the company's claim that the mean body temperature hadn't changed, because it obviously has changed. All right, so don't worry too much about that one. You cannot get that from your Z tables because it doesn't go beyond 3 in the Z score readings. But anyway, you can take from that it's pretty much the entire population, because it's very unusual to get Z score readings beyond plus and minus 2 standard deviations above and below the mean.